In earlier lessons, we've discussed the idea of momentum. Momentum is a physical property of moving objects, and it's the product of the mass of the object times its velocity. Right? And when you deal with momentum, you're typically thinking of objects colliding and transferring momentum. And what we need to understand is that when we have that collision, the system, the objects colliding, well, the momentum of that system before the collision is equal to the momentum of the system after that collision, right? So this is how we would set up problems. We use conservation of momentum to find the velocities before and after of different objects. Now, we also learned that there's different types of collisions, right? Momentum's always conserved, but in some collisions, we lose some energy, right? So we have two types. We have elastic collisions, and we have inelastic collisions, right? And if you think elastic, bouncy, inelastic, not bouncy. Well, inelastic, therefore, has the scenario where the kinetic energy before the collision is not the same as the kinetic energy after the collision, right? We lose some energy in that collision, and because we're not bouncy, we're inelastic. Now, it doesn't mean they won't bounce at all. It doesn't mean they lose all the kinetic energy, but kinetic energy is not conserved. Whereas an elastic collision is defined as kinetic energy before the collision being equal to the kinetic energy after the collision, right? Kinetic energy is conserved. We can use 1/2 mv squared on both sides, and it should match out. Now, in the real world, elastic collisions are rare because you're always going to have some kind of sound or heat or friction. So most collisions really fall under the category of inelastic. And then there was a subset of inelastic collisions where the objects actually stick together and move as one object, and we call that a completely inelastic collision. Sometimes a perfectly inelastic collision. That's just where the objects finish as one object, or kind of the reverse of that would be like firing a gun or an explosion where objects start together and those masses end up apart with various velocities. All right, so this is what we've been doing to solve problems up to this point, is using momentum. Now, what we haven't gone into is, well, how do we get momentum in the first place? And this ties back into some of Newton's laws. And Newton really understood momentum, and that was the foundation of his three laws. So these are some concepts we should already be familiar with, but let's talk about how an object can change its momentum, right? So how can we change an object's momentum? And I hope intuitively you would say, well, we're not changing the object's mass. That would change the object itself, right? So really the only variable we can change would be to change its velocity. And we've changed velocity before. What does it mean to change velocity? We can accelerate it. And how do we accelerate something? Well, we push on it, right? So an acceleration is really caused by a force, so we can apply a force. Right? An unbalanced force causes an acceleration, and the longer I accelerate, the faster I go, or the more I slow down if I'm getting a push, right? So we know that time is a factor, right? So if I apply that force for more time, sorry for my mouse being a little funny here. If I apply it for more time, we get a greater or more change in momentum, really change in velocity. Greater change in velocity. And in turn, momentum. So if I have an object and it's moving, I can push on it and make it move faster and increase its momentum, or I can push against its motion, slow it down, and take away its momentum. Right? And in a collision, that's what that other object is doing. It's colliding with that moving object and changing its velocity. All right, so this is a concept hopefully we can connect with Newton's laws. But let's write this out as an equation here. Change in momentum would be a change in P. And a change in momentum, therefore, is equal to the mass times velocity, but not just the velocity, but the change in velocity, right? So this would be change in momentum. That's what that delta is change in. So a change in momentum is caused by a mass times a change in velocity. But we know something about change in velocity. Well, that's an acceleration. An acceleration is a change in velocity over time. And so we can write that change in velocity is just acceleration times time. And if we want to substitute that right into here, we get a new equation that says that delta P, the change in momentum, is equal to mass times acceleration times time. Right, so just another variation on that same equation. And I hope you recognize m times a. Well, what is that? Well, Newton's second law says that is force, right? Or the net force or the unbalanced force. And that gives us our typical equation for change in momentum, which is force times time. And this equation or this concept is what we call an impulse. An impulse is a force applied over a period of time, and it is what causes a change in momentum. So we'll define impulse. So if something gets an impulse is defined as a change in momentum. And change in momentum is delta P, also called an impulse. Or we can define an impulse as a force applied over a period of time. And that would be F times T, which is the other side of that equation. Right? So we have a force applied over a period of time or a change in momentum. This is what we call an impulse. Right? And so when we look at the equation for impulse, you see different variations. Right? I can say that an impulse is equal to a change in momentum, but it is also equal to a force times the time. Now, change in momentum is just P final minus P initial, what the later momentum is minus the earlier. And that would be the mass times the velocity final minus the mass times the velocity initial. Right? And we can look at that as the mass times V final minus V initial if I want to factor out an M, right? So you have all these different variations. If I know the mass, the two velocities, if I know a force, a time, these are all ways I can find an impulse, right? And if I want to look at units, just to tie it all together, what's the unit of an impulse? Well, it better be the units of a force times a time. That's a Newton second. It also needs to be the same as the units of momentum, which is a kilogram times a meter per second. Right? Well, those are the same thing. These are the same units, right? Because remember, if I take a Newton is a kilogram times a meter per second squared, an M times an A, and I multiply that times a second, we see that the seconds cancel and I get a unit of momentum, or sorry, a Newton second, a unit of momentum right here, right? So these are the units for impulse. So now let's take this concept and apply it here. Here we have an example problem, right? Really typical type of problem here where we're looking at an object that experiences an impulse. And we know it experiences an impulse because its velocity changes and therefore its momentum changes. When you're solving problems with momentum, we're typically looking at collisions between two objects. When we start looking at what one object is doing alone without knowing something about the other object, well, then we're back to thinking about an impulse rather than conservation momentum. So in this case, they don't say anything about the bat, other than there's a collision with a bat. The bat is applying a force. But we know something about this fastball. This baseball is thrown with velocity. Its velocity changes over a period of time, and we should be thinking impulse. Right? So in this case, it's thrown from the pitcher towards home plate. It's hit by the batter and exits the bat going the opposite direction, going faster. There's a big speed change, right, from positive to negative. And it happens over a short period of time, right? So we can be able to identify, hey, there must be a large force on this baseball due to this collision. Well, like everything else, let's start with a picture. All right, here's my initial situation. I have the baseball, and it has velocity. Let's say that positive is the rightward direction. It's always a good thing to define. So it's got a 40 meter per second velocity. It's about roughly 90 miles an hour. And there's a collision, right? And I'll just draw this bat in here. And this bat has some kind of velocity this way. We don't know that, right? But that's what's happening right before the collision. Now, after the collision, we now know that this ball has hit the bat and it is now traveling faster and moving the other direction, right? So I'll draw that arrow in here and I'll label it as 50 meters per second. Coincidentally, that bat collision that happened here, right? This bat is probably still moving that way, but hopefully with conservation of momentum, you would infer that that bat has slowed down. So I'll draw a little smaller arrow. I don't know anything about the speed of the bat. If I did, I could predict what that would have to be. But all we care about right now is the baseball. Well, let's start tying some things together here. All right. We know that that ball experienced a change in momentum, which is equal to the force applied on that ball over a period of time. All right. Well, what variables do we have? Well, we know the mass of the ball. They told us it is 145 grams. Be careful. We always want to be in kilograms, right? Well, 145 grams is 0.145 kilograms. They tell you the time of the collision of 0.05 seconds. We know the initial velocity of the ball, and we know the final velocity. Well, it's moving to the right. Let's put a positive there. Sorry, to the right at 40 meters per second. And later it's moving to the left at 50. There's our negative. Be careful with those signs. So that's the information given in the problem. Initial final velocity, a mass, a time, right? And we want to know, well, what is the force of the bat on the ball? All right, that's the unknown that we're trying to find. So I've organized my thoughts. I've got one unknown. That's good. I got an equation for impulse, but I see delta P. Well, what is delta P? Well, delta P is just my final momentum minus my initial momentum, and that is equal to force times time. But delta P is also a mass times a change in velocity. Mass times delta V is also an impulse, right? So that might actually be a better variation. And mass times delta V is really just mass times V final minus V initial. That's what delta V is, right? And so now I have a new equation I've derived, and I have all the pieces for this, right? I have the mass, I have the velocity, I have everything except the force. And so now let's plug in those values and see if we can identify what we're going to have here, right? So in that equation, I have now my mass, which is 0.145 kilograms. I have my velocities. V final is negative 50 minus positive 40, right? So I get a change in velocity of 90 meters per second, a big change in velocity, right? So if I simplify this side, I get something like this on the left side, and that's equal to the unknown force times my time of impact. So this has to equal F times 0.05. All right, so I've got this equation. I've simplified it down. If I take now that value of 145.145 times 90, I get 13.05. There is a change in momentum to the left at 13.05, and that is equal to that force times 0.05. And now I just need to solve for F. I'm going to divide by 0.05 on both sides. And when I get that, I get a force, right, of 261 newtons. Right? I get an answer that's to the left at 261 newtons. That is the force of the bat on the ball. All right, and that means it is to the left, which is what I expect based on how I drew my picture. All right, look at my picture. I expect that that ball is being pushed to the left by the bat, and we get 261 newtons of force. All right, so we've now used impulse to define exactly the force on that ball. Now, in summary, this should also remind you of something else here, and I wrote it this way: bat on ball. If you recall, Newton's third law talks about equal and opposite force pairs. Well, shouldn't that ball apply a force on the bat? And what would that force be? Well, Newton's third law suggests that there is a force of the ball acting on the bat as well. And notice I just switched the order of those. And that force, according to Newton's third law, would have to be in the opposite direction, but with an equal amount. That bat is going to experience a rightward push by the ball. And as a result of that, the bat is going to decelerate. It's going to slow down, right? And we see in our picture that we drew a shorter arrow. Now, that amount of force it's going to feel will actually slow it down less, though, because that mass of the bat is probably much bigger. All right, so it's going to keep moving. There's a transfer of momentum here. Momentum's conserved in the collision, and those objects experience the same force due to that impact. All right, so it's a good classic example of a collision. We could break this down further. We can identify, if we knew the velocity of the bat, we could figure out, well, what is its change in velocity? We could figure out some other pieces if I had other information. But right here, this problem only cares about the baseball. We know the velocities. We know its change in momentum, and therefore we can find the force of the ball on the ball by the bat.